The 1927 Solvay conference is famous for its iconic photograph featuring 29 of the world's leading physicists, including 17 who either were or would become Nobel laureates. In this photograph, Lorentz and Einstein are seated prominently in the front row, signifying their importance in the field. Hendrik Lorentz shared the 1902 Nobel Prize in Physics with Peter Zeeman for the discovery and theoretical explanation of the Zeeman effect. Albert Einstein, on the other hand, was awarded the Nobel Prize in 1921 primarily for his discovery of the law of the photoelectric effect. While Hendrik Lorentz and Albert Einstein did not formally collaborate on specific scientific projects or papers, their interactions and mutual influence were significant in the development of modern physics. Most significantly, special relativity, the subject of this video. Special relativity, developed by Albert Einstein in 1905, rests on two pivotal postulates. That the speed of light is an absolute constant in space, and the invariance of physical laws across all inertial frames of reference. However, the seeds of special relativity were sown earlier by Hendrik Lorentz. Lorentz's meticulous work on electromagnetic theory and the formulation of the Lorentz transformations provided the mathematical backbone for Einstein's insights. While Lorentz explored how objects contract and time dilates at high velocities, it was Einstein who fully realized and unified these ideas, revealing that time and space are intertwined in a four-dimensional continuum. The postulate that the speed of light is absolute is a revolutionary idea. It means that it is constant regardless of the motion of the observer or the source of light. This stands in stark contrast to the Galilean transformation, and special relativity requires a new transformation which ensures the constancy of the speed of light. It also means that space and time are no longer separate, rather they forms a continuum called Minkowski spacetime. In this video I shall prove to you with simple arguments the form of the Lorentz transformation, which one can derive by assuming that the speed of light is the same across all inertial frames of reference. In the second half of this video, we elucidate on a geometrical approach to the understanding of Minkowski spacetime. As we shall see, Lorentz transformation can be mapped onto hyperbolic geometry, allowing for very intuitive picture of spacetime transformation, which can be particularly useful in understanding of well-known phenomena in special relativity, such as time dilation and length contraction. Let's begin. The principle of relativity versus special relativity.
What does relativity mean? Relativity means that for all coordinate systems which are related to each other by uniform velocity, all reference frames related to each other by uniform motion, the laws of physics are the same. The laws of physics are the same in every reference frame. The word is inertial reference frame. You know the term inertial reference frame. If one frame is inertial, then any frame moving with uniform velocity relative to it is inertial. What is an inertial reference frame? What is the first inertial reference frame that you start with? Let's just make it simple and say it's a frame of reference in which Newton's laws are correct, and in particular, where particles which have no forces on them move with uniform velocity. That's a reference frame. Every frame moving uniformly relative to it, not rotating relative to it, not accelerating relative to it, is another inertial frame. And it's a feature of Newtonian mechanics that the laws of physics, F equals ma, that together with Newton's law of attraction or Coulomb's law of attraction, they're the same in every reference frame. So if you like, the way I like to describe this is, go to the proverbial railroad train moving down the x-axis with uniform velocity, and think about you or me. I'm in the train, you're standing still. You have a set of laws, and the way I like to think about it is laws of juggling. Juggling is a good thing that makes a lot of use of classical mechanics, inertia, forces, all the good stuff. And if you know how to juggle at rest, you juggle exactly the same way in the moving reference frame. Right? You cannot tell. Another way to say it is if you're in a moving reference frame. If I'm in a moving reference frame and everything is sealed so that I can't see outside, I cannot tell that I'm moving. I try to find out by doing some juggling, and I find out that my standard laws of juggling work, and I assume, therefore, that I'm at rest. But that's not right. All it tells me is that I'm in uniform motion. So the principle of relativity is that the laws of physics are the same in every reference frame. That principle existed before Einstein. It was not invented by Einstein. Sometimes it's attributed to Galileo. I don't know if he said it or not. Newton would have recognized it. And it is called the principle of relativity. What did Einstein add? Einstein added one law of physics. The law of physics is that the speed of light is the speed of light, c, that the speed of light is 186,000 miles per second, or that the speed of light is 3 times 10 to the 8 meters per second. That's a law of physics. Now, if you combine the two things together, that the laws of physics are the same in every reference frame, and that it's a law of physics that light moves with a certain velocity, you come to the conclusion that light must move with the same velocity in every reference frame. Why? Because the principle of relativity says the laws of physics are the same in every reference frame, and Einstein announced that it's a law of physics that light moves with a certain velocity.
Relative speed in Galileo's world versus the speed of light is absolute.
Well, first off, speed is a concept that even before Einstein was known is a concept that is relative. What do I mean by that? Well, imagine we look at this car, say it's going 100 kilometers per hour. What we need to say is 100 kilometers per hour relative to the road. Why? If that road is itself moving, let's say it's on a boat, the boat is moving, then the car's speed relative to the water is not 100 kilometers per hour. And if we zoom out and look at that car on the surface of the Earth, and we realize that the Earth itself is spinning around, the Earth itself is going in orbit around the Sun, with respect to the frame of reference, our perspective right now, that car is executing a pretty complicated motion, not just 100 kilometers per hour. So it's always vital when you're talking about speed to recognize that you can only ever frame the idea of speed for ordinary objects that we encounter as the object has this and that speed relative to this or that object. You need to specify the reference in order that the speed that you are specifying has any meaning at all.
The debate about whether the speed of light is relative or absolute spans over many decades, but there were two most notable evidences staring at Einstein. In 1887, Albert Michelson and Edward Morley set up an interferometer to measure the difference in the speed of light in opposing directions to the Earth's rotation. Their experiment failed to detect any such difference, leading to the suspicion that the speed of light is constant regardless of the observer's motion. In parallel, the development of electromagnetism also lends credence to the idea that light is an electromagnetic wave and travels at a constant speed in space. Brian Greene summarized these most beautifully in his lectures.
Maxwell had these equations, and from the equations out came, from a calculation, a speed that was equal to the speed of light. What was Maxwell to conclude? Well, naturally, he said, if the speed of the electromagnetic disturbances is equal to the speed of light, then light itself must be an electromagnetic disturbance. It must be an electromagnetic wave. That was a great step forward. Now we had an understanding of what light actually is. But even with the progress that that represented, it still raised a profound mystery. And that mystery is this. As we described before, whenever you talk about speed, you need to say an object has this speed relative to that object. You need to state things in that manner for speed to even have any meaning, right? But when it comes to the equations that Maxwell was studying, they didn't specify what speed 671 million miles per hour was relative to, right? So if you have sound waves, the speed of sound is relative to the still air. If you've got water waves, the speed of the water wave is relative to the still water. What was the thing relative to the speed of light was being calculated? Nothing seemed apparent, so physicists dealt with this mystery by making up an answer. They said maybe there is something called the ether filling space, and when you talk about the speed of light, you're talking about the speed of this electromagnetic wave relative to the ether. Experiments were done to try to find the ether, and to make a long story short, no evidence for the ether whatsoever. So the puzzle remained. This is where the genius of Einstein comes into the story. Because Einstein had this uncanny ability to look at something that everybody else had been staring at and see it in a new way. And Einstein said, look, if the equations are saying that the speed of light is 671 million miles per hour, but the equations are not specifying what that speed is relative to, maybe that's because you don't need to specify anything. Einstein said the speed of light is 671 million miles per hour relative to anything, so long as it is traveling through empty space. Now, this is a strange idea. It is a maverick idea. You might say it's a crazy idea because we are unused to any speed that isn't relative. We are unused to any speed that, for instance, can't be changed by running toward it or away from it. But that is what Einstein was saying.
For conceptual clarity, we shall go to the blackboard and introduce an important tool in the visualization of spacetime. Consider an inertial frame, and let's call it to be that of Alice. Here, t represents time, and x represents the spatial dimension. To keep things simple, we shall consider the spatial dimension to be 1D. From Alice's perspective, she is stationary, so her world line is just a vertical line given by x equals 0. The world line depicts the path the object takes through spacetime. Now enters Bob, who is moving at constant velocity v relative to Alice in the direction of x. The world line for Bob, in Alice's frame, would be a straight line with a slope characterized by the velocity v. The angle of the world line thus denotes the speed of the object. 0-degree angle means stationary, while 90 degrees means infinite speed. The speed of light on this scale would then appear to be almost horizontal. Now let's consider the reference frame for Bob, denoted by the space-time coordinates x bar and t bar. From Bob's perspective, he viewed himself as being stationary, thus x bar equals 0. This statement that every observer is stationary with respect to himself is an obvious fact. Thus, this holds not just in classic Galilean transformation, but also in the new transformation that we are seeking. It will be mathematically convenient, as we shall see later, to define the time coordinates with the same dimensionality as the spatial coordinate by multiplying it with the speed of light c. The world line for light would then be a straight line with an angle of 45 degrees. The Galilean transformation describes how the coordinates of an event change between two reference frames moving at a constant velocity relative to each other. It asserts that the time coordinate remains unchanged, while the spatial coordinates transform linearly based on the relative velocity and time given by v times t bar. Mathematically, the Galilean space-time transformation can be expressed in simple matrix form as follows, where the transformation matrix G can be written explicitly as shown. As it is apparent, simple Galilean transformation would require that the speed of light to be reduced by an amount v in Bob reference frame. Thus, a different transformation must be devised if we want the speed of light to be constant irrespective of all inertial frames. Lorentz transformation is a linear transformation of spacetime that respects the existence of such a speed limit. General structure of the Lorentz transformation matrix. In previous chapter, we obtained the Galilean transformation matrix and have seen that speed is always a relative concept, including the speed of light. What we want to achieve in this chapter is to derive the form of the spacetime transformation matrix, L, which leaves the speed of light c unchanged. Such a transformation is called the Lorentz transformation. Let's go back to our blackboard and bring in Alice and Bob, with Bob moving at a speed v relative to Alice. We sketch the spacetime diagrams for these two inertial frames, including the light cone or the world line of photons. We seek to find the form of the transformation, where the world line of the photon, or a particle traveling at the speed limit, is invariant under this transformation. This transformation can be represented by a 2x2 matrix L in this case, and is called the Lorentz transformation. In the next few minutes, we shall derive the general structure of the matrix L. Now, consider an event on the light line given by the spacetime coordinate 1, 1. Since the speed of light is an invariant, the Lorentz transformation would map the event back onto the light line. The new spacetime vector is then merely scaled by a positive constant, herein denoted as alpha. Thus, we can write the Lorentz transformation in the familiar mathematical form, where the vector 1, 1 is the eigenvector and alpha is the eigenvalue. Since L is a 2x2 matrix, we expect that it has another eigenvector that together spans the R2 space. The second eigenvector describes photons moving in the opposite direction, whose eigenvector is given by -1, 1 instead, where alpha is again a positive number. The eigenvector equation is then given as follows. However, we stress that the alphas in the positive and negative velocities world line need not be the same. Taking this into consideration, we shall denote the eigenvalues for the forward and backward propagating photons as alpha plus and alpha minus respectively. Basic linear algebra then allow us to express the Lorentz transformation matrix in terms of its eigenvectors and eigenvalues, based on the spectral decomposition theorem. Simple, straightforward algebra then allow us to express the Lorentz transformation matrix in a 2x2 form, where gamma and beta are related to the eigenvalues alpha plus and minus. In special relativity, gamma is typically called the Lorentz factor, and beta is the velocity parameter. We shall discuss the physical meaning of these two parameters in the next chapter. Feel free to pause here if you would like to inspect the math. In summary, if two inertial frames are moving at constant velocity v relative to one another, the transformation that ensures that the speed of light is invariant under the transformation is known as Lorentz transformation, which is a linear operation and has the structure as shown, where the Lorentz factor gamma and the velocity parameter beta are to be determined in the next chapter. Determining the Lorentz factor gamma and the velocity factor beta. Starting from where we left off in the previous chapter, we have derived the structure of the Lorentz transformation matrix, but gamma and beta are yet to be determined. Let's first work out what is beta, the velocity parameter. Let's begin with the inertial frames of Alice and Bob and the world line of photon in these two frames, which we know is invariant under Lorentz transformation. In other words, c is a constant under Lorentz transformation. Bob is moving at a constant velocity v with respect to Alice. We draw Bob's world line in Alice's spacetime diagram. Since every observer is stationary in his own reference frame, Bob's world line in his spacetime diagram would just be a vertical line as shown. Now, let's try to express this basic fact in its mathematical form. We have the Lorentz matrix operating on the spacetime coordinates of Bob in Alice's inertial frame. Since Bob's world line is given by x equals to v times t, we can replace x with v times t. The Lorentz transformation into Bob's inertial frame would transform into a vertical world line, where the x bar is 0 for all t bar. This equation is nothing but a mathematical statement that every observer is stationary with respect to his own inertial frame. We also use this fact in Galilean transformation discussed in Chapter 2. From this matrix equation, one also have the following relation for beta, from which an expression for beta can be obtained. Thus we have showed that beta is simply equal to the ratio of V to C. Note the minus sign in the definition of beta. Of course, one could also pull out the minus sign and incorporate it into the Lorentz matrix instead, which is what is often done in the literature. In this video, we shall use the former convention instead, as shown. Next, how about the Lorentz factor gamma? To solve this, we shall use an insight from Einstein, best explained by Leonard Susskind.
I haven't read it for probably 50 years, but it has left, obviously, a very lasting impression on me. This is basically what he did in that first paper. Well, this and a lot more. Okay. So now he said, wait a minute, who's to say which frame was moving? Who's to say if my frame is moving relative to you with velocity v, or your frame is moving relative to me with velocity minus v? Whatever the relationship between the two frames of reference are, they should be symmetrical. We could take the entire argument, and instead of starting with the x and t and drawing an x prime and t prime, we could do exactly the opposite. The only difference would be that, as far as I'm concerned, you're moving with velocity minus v. As far as you're concerned, I'm moving with velocity plus v.
Okay, here is what Leonard Susskind is saying. Previously, we wrote down the Lorentz transformation between the two inertial frames, where that of Bob's is moving at speed v and Alice's frame is stationary. However, since no one inertial frame is more privileged than the other, we could have considered Bob's frame to be stationary, while that of Alice's is moving with velocity v in the opposite direction. Then, we can similarly write down the Lorentz transformation of the stationary frame to the moving frame as follows. Note how the coordinates vector of the two inertial frames are swapped in these equations, while the negative signs are due to the opposite velocities v in these two perspectives. Focusing on these two equations, we see that the spacetime vector in the top equation can be replaced with the expression in the bottom equation, which yields us the following. Since the spacetime vector on both sides of the equation are the same, the matrix expression as highlighted must be equal to unity. It is then straightforward to show that the Lorentz factor gamma is given as follows. Feel free to pause the video if you would like to inspect the math. In summary, we have successfully derived the expression for Lorentz transformation. The spacetime interval, the invariant of Lorentz transformation. If the laws of physics are invariant under certain transformations, then there is a corresponding quantity that remains constant over time. What is the invariant quantity under Lorentz transformation? That is the focus of this chapter. Let's begin with a very classic transformation in Euclidean geometry, namely that of rotation. The rotation matrix R for a two-dimensional Cartesian coordinate system is given as follows, which rotates points counterclockwise through the angle theta about the origin. With increasing theta, these points traces out a circle, and the distance of these points from the origin is an invariant herein denoted by the distance L. The formula is the well-known Pythagoras theorem. Now, what is the invariant associated with Lorentz transformation in spacetime? Hermann Minkowski made breakthrough understanding to this fundamental question. In 1907, he considered space and time, which was previously thought to be independent, as a four-dimensional spacetime continuum and formulate the geometry of spacetime under Lorentz transformation. Minkowski realized that the geometry of Lorentz transformation in spacetime is very different from that of rotation transformation in Euclidean geometry. The Lorentz transformation, which acts on spacetime, has the following structure which we derived earlier. Minkowski first showed that Lorentz transformations are hyperbolic rotations that leave the hyperbola invariant and rewrote the Lorentz matrix as follows. Minkowski also introduced the quantity called spacetime interval as the invariant of Lorentz transformation in spacetime. This geometric interpretation provided a deeper insight into the nature of spacetime and the behavior of objects moving at relativistic speeds. In the remaining of this chapter, we shall focus on proving these two mathematical results. First, we will derive the hyperbolic form of the Lorentz transformation matrix. Here is the Lorentz matrix, where beta is the velocity parameter and gamma the Lorentz factor, which can be expressed in terms of beta. We see that the diagonals and off-diagonals are both symmetric, and the difference of their squares equals 1, which is the very identity for gamma. This type of identity can be found in hyperbolic trigonometric functions. Here, gamma can be replaced with hyperbolic cosine, a positive definite function, just like gamma itself. On the other hand, gamma times beta can be replaced with hyperbolic sine, an asymmetric function just like beta. With this replacement, the Lorentz transformation matrix can then be expressed in the form of a hyperbolic rotation as function of the parameter theta. The hyperbolic angle, theta, can then be determined from the inverse hyperbolic tangent of beta, as shown. Great. The mathematical proof is straightforward. Next, let's see what this means. Let's start with the spacetime diagram and see what the Lorentz hyperbolic rotation does to an event. But first, let's indicate on the plot the light line. Consider an event in spacetime. The parameter theta controls the Lorentz boost onto an inertial frame moving at velocity v along the x direction. So how does the Lorentz transformation rotates the event in spacetime? Since this is hyperbolic rotation, rotation has a very different meaning here compared to rotation in Euclidean geometry. Instead, rotation with increasing theta traces out a hyperbolic curve as shown. One might then guess that the spacetime invariant has something to do with this hyperbola. Indeed, the invariant, which is also called the spacetime interval, is given by the equation of a hyperbola, as shown. For each value of s, we have a different hyperbola. When s squared is 0, the hyperbola equation yields us the light line. Recall that the speed of light is an invariant in Lorentz transformation. Thus, an event on the light line will simply be translated along this line under the Lorentz transformation, or hyperbolic rotation. Thus, unlike Euclidean geometry where rotation traces out a circle, Lorentz transformation traces out a hyperbola. Each s squared corresponds to a hyperbola, and when s squared is 0, it yields the light line. Lorentz transformation of an event traces out a hyperbola, while keeping the spacetime interval, s squared, invariant. We shall talk more about spacetime rotations in the last chapter. We shall end this chapter by giving a mathematical proof of the invariance of spacetime interval. We begin with the equation for Lorentz transformation. Recall also the relation between gamma and beta we derived earlier. We write down explicitly the system of equations represented by the matrix equation for Lorentz transformation. We want to show that the spacetime interval in this Lorentz transformed spacetime coordinates is the same as that in the original spacetime coordinates. This is indeed the case, as one can show with simple algebra. Feel free to pause the video if you would like to inspect the math. Great. We have shown that Lorentz transformations can be understood as hyperbolic rotations in spacetime, analogous to rotational transformations in Euclidean space. We also showed that Lorentz transformation ensures the invariance of the spacetime interval, a quantity that remains constant for all observers regardless of their relative motion. In this chapter, we shall say a few words about the concept of distances by making connection to the well-known Pythagoras theorem. In the November 26, 1949 issue of the Saturday Review of Literature, Albert Einstein, at the age of 67, penned down some notes for an autobiography. As Einstein put it, he was writing something akin to his own obituary, reflecting on key events in his lifelong strive and search for the truths of our universe. Albert Einstein's scientific career was deeply influenced by the principles of geometry, particularly the Pythagorean theorem, which states that in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. This fundamental idea plays a crucial role in the geometry of spacetime, which is central to Einstein's theories of relativity, as he recollected in this autobiography. Let's start with the Euclidean geometry. Consider a vector r in 2D Cartesian coordinate system and break it down into components of the basis vectors x and y hat. In Euclidean geometry, the square of the length of the vector r square is given by the dot product with itself. R square can then be written in the following compact form, where the matrix is highlighted is called the metric tensor. This is a fundamental object in differential geometry that defines the distance between 2 points in a given space. In Euclidean geometry, with orthonormal basis, the metric tensor is just the identity matrix. The familiar form of the Pythagoras theorem, r square equals to x square plus y square, emerges naturally from this definition of length. Feel free to pause the video if you would like to inspect the math. Now, what if we have non-Cartesian axes, where the bases are not orthonormal? Then, in this case, the metric tensor would not be the identity, and the Pythagoras theorem which one uses to compute the distance between any 2 points would have to be modified. In relativity, the concept of metric extends also into the realm of differential geometry to describe the curvature of spacetime. Minkowski spacetime is a 4-dimensional construct that unifies space and time into a single continuum. For our purpose here, it suffices to just consider the space as one-dimensional. We can characterize the spacetime displacement by the vector s, expressed in terms of the time and spatial basis vectors. The notion of magnitude for spacetime displacement is called the spacetime interval, s. We expressed in a similar form where the metric is made explicit. Here, the Minkowski metric tensor is not an identity matrix, rather the time element has an opposite sign, of -1 in this case. The spacetime interval, defined by the Minkowski metric, thus yields a different form of the Pythagorean theorem, which expresses the relationship between space and time coordinates of events, and providing a geometric interpretation of the effects of relativity. The last chapter, Euclidean versus spacetime rotations. Quick recap. We showed that rotation of a point in Euclidean space traces out a circle, which keeps the distance with a point at origin invariant. The notion of Euclidean distance is given by the familiar Pythagorean theorem. In Minkowski spacetime, we showed that Lorentz transformation is analogous to hyperbolic rotations, whose rotation traces out a hyperbola, which keeps the distance to the origin invariant. The notion of spacetime distance is given by the non-Euclidean Pythagorean theorem, denoted as s. In other words, all points on this hyperbola has the same s square. The hyperbolic angle is related to the velocity parameter, thus is a measure of the velocity boost of the reference frames. These geometric transformation of points are called active transformation. However, one can instead perform passive transformations, which leave points fixed but change the frame of reference or coordinate system relative to which they are described. Here we illustrate with the rotation operator in Cartesian coordinate system. Clearly, regardless of the different reference frame, the distance of the point from origin is invariant for each observer. The coordinates varies as it depends on the choice of axes or basis, but the invariant is something all observers in the different coordinate systems agreed upon. It can be checked that the determinant of the rotation operator is 1, hence the basis vectors preserve the area, as illustrated by the gray squares. Here is the analogous passive transformation for Lorentz transformation in terms of the hyperbolic angles. Unlike the previous example for Euclidean geometry, the two space-time axes rotate toward each other symmetrically in a scissors-like way, while keeping the light line invariant. This transformation involves axis scaling, where the time and spatial coordinates are adjusted to account for relative motion. A key consequence of the Lorentz transformation is time dilation, where a moving clock runs slower compared to a stationary one. Another important effect is length contraction, which means that objects moving at high speeds appear shorter along the direction of motion to a stationary observer. These phenomena are fundamental to the theory of special relativity and ensure the constancy of the speed of light in all inertial frames. Similarly, the determinant of the Lorentz transformation matrix is 1, hence the basis vectors preserve the area, as illustrated by the gray rectangles. With this, I hope this video achieved the goal of explaining the key concepts related to Lorentz transformation. These tools will set the stage for the sequel to this video, where we will discuss physical phenomena such as time dilation, length contraction, and simultaneity. Lastly, if this video motivates you to want to learn more about special relativity, check out the excellent lecture series by Leonard, Susskind, and Greene on YouTube.